Hi, I'm Mark Barsamian. In the previous video, I discussed the closed interval method for finding the absolute extrema of a function on a closed interval. In this video, I'll be discussing techniques for finding absolute extrema of a function on a general interval. One of the things that we'll learn about is the second derivative test for finding local extrema and absolute extrema. This material is from section 4.5 of the book, more specifically pages 299 to 302. Examples 2 and 3 correspond to the material in this video. The corresponding homework is this collection of exercises from section 4.5. The asterisk on this problem indicates that it's not in the MyLab system, but it's a good problem and it's good to study. I'll actually be doing an example that's similar to that problem number 53 in the video. Let's review some stuff from previous videos. We discussed the definition of critical numbers from section 4.1 in the video for homework 55. A critical number for a function f is an x value that has two properties. The first property is that either f prime parentheses c is 0 or f prime parentheses c does not exist. That means that the x value is a partition number for f prime. And the other property is that f of c exists. That means that the number x equals c is in the domain of f of x. And recall the definition of absolute extrema from section 4.5, which was introduced in the video for homework 61. An absolute max is a y value for a function that has the property that for all x's in the domain of the function, that y value is greater than or equal to all the other y values. Similarly, for an absolute min is a y value such that for all x's in the domain of the function, that y value is less than or equal to the other y values. And recall from the video for homework 61, this example that illustrated that absolute extrema do not always occur. We have a number of intervals such as this one, that green chunk of the graph without its endpoints. Number of intervals like that where an absolute max or min did not exist. But there was one important situation where both the absolute max and absolute min are guaranteed. That was the case of a function f that's continuous on a closed interval. A function like that has both an absolute max and an absolute min on the interval. So that interval of the graph, from 6 to 15 with the endpoints, had both an absolute max and an absolute min. And there was a theorem that tells us where those absolute extrema have to occur. They have to occur at critical numbers or at endpoints of the domain. So in the previous video, we discussed what's called the closed interval method for finding the absolute extrema on a closed interval for a function that's continuous on that interval. It was this procedure. But what about the situation where the domain of the function is not a closed interval? How do you determine the absolute extrema that do occur? Well, as we'll see in this video, that question is answered in different ways for different functions. For some familiar function types, the approach can be to first consider the end behavior to determine what kinds of absolute extrema will occur, and then find the locations of the extrema that you do know are going to exist. For our first example, which is similar to these two homework exercises, we'll consider this function that is a fourth degree polynomial. Question A is to find all absolute extrema of f of x on the interval negative infinity to infinity. Well, notice that that is not a closed interval. So we're not guaranteed that there will be any extrema. So back to what I said on the previous page, in some familiar function types, the approach can be to consider the end behavior to determine what kinds of absolute extrema will occur. Well, what is the end behavior? Well, what do we look at? We look at the degree of the polynomial, so it's an even degree polynomial. And what else do we look at? We look at the sign of the leading coefficient. We have a negative leading coefficient. So those two things tell us that the graph will go down on both ends. Now, when I say down on both ends, I mean it just keeps going down. So something like this. Now, what happens in the middle? Well, we can see that f is a polynomial, so it's continuous, so there are no jumps or breaks or gaps in the graph. It'll have no breaks or jumps or asymptotes. It'll just have some wiggles, and we can see that since it's a fourth degree polynomial, it could have as many as 3 turning points. So we can see that the graph can have a shape like this. So we can see that there will be no absolute min, but there will be an absolute max, for sure. There will be no lowest point on this graph, but there will be a highest point. So let's go back to what I said on the previous page. That's an example where we considered the end behavior to determine which kinds of absolute extrema will occur. Now notice we didn't have to do any calculations on this page. We've already figured out that there is no absolute min without having to do any calculations. That doesn't mean that what we did is easy. I mean, there's a lot of thought that went into knowing that this is a way to approach the problem. There's some experience with functions that makes you look at a function like this and realize, oh yeah, that's a graph that's going to look like this. So easy in terms of calculations, hard in terms of having to have some experience and good eyes to see that that's the way you approach this problem. So we know there won't be an absolute min, there will be an absolute max. Now we need to find them. We'll do that on the next page. So where do we look for the absolute max? Well, the key here is to remember Theorem 2. Theorem 2 says absolute extrema, if they exist, must occur at critical numbers or at endpoints. In our example, we don't have endpoints, so if there are going to be any absolute extrema, they're going to have to occur at critical numbers. Well, we've determined that there's going to be an absolute max, so Theorem 2 tells us that it's going to have to occur at a critical number. So we have to find the critical numbers for f of x. So there are the critical numbers for f of x. We found f prime, we set f prime equal to 0, and solved for x. We found those 3 x values. Now, what do we do with these? Well, we know that there's going to be a max, and it has to occur at one of these x values. So we just simply find the y values at these x values and see which one is the biggest. We'll do that on the next page. So there's our result. Those are the y values at those 3 x values. Now we know that there's going to be a max, so it's going to have to be one of these y values, and that's it. So we see that that is the absolute max. We see the absolute max on this interval is the y value y equals 194, and it occurs at the x value x equals -3. Now it's worth saying again that there is no absolute min on that interval. So there's our conclusion. Again, we first reasoned that there had to be an absolute max and there would not be an absolute min, and then we used Theorem 2 to tell us that the absolute max would have to occur at a critical number. So we found the critical numbers, and there were 3 of them, and we compared the y values at those 3 critical numbers. There were these 3 y values. Now notice that I did not go through the details of these calculations here and here. This is arithmetic. It's a prerequisite for this course. Now, it's important to realize that this list of y values is just like the list of y values that we used in the previous video when we were looking for absolute maxes and absolute mins. When we were doing the closed interval method, we looked at lists of y values. We picked the greatest one on the list to be the absolute max, and we picked the least one on the list to be the absolute min. Well, it would be tempting to look at this list of numbers here and say, oh, look, that 5 is the least one on that list. That's going to be the absolute min. But realize, again, we already knew that there was not going to be an absolute min. So that's why it's important in these problems to start by figuring out what you expect to find. We expected to find an absolute max, and we knew there was not going to be an absolute min. So even though this number 5 is the smallest number on this list, it's not the absolute min for our function. There is no absolute min for our function on this interval. Let's go on. Question B is, find the absolute extrema of the function on this interval, -2 to infinity, with the endpoint -2 included. Well, the solution to this is to do exactly what we did before. Think about whether we expect there to be absolute maxes or mins, and then find them. So we had, in question A, reasoned that the graph was going to look something like this. Now, we have cut off the left end of the graph because we're looking at this half-open interval. But the right end of the graph still goes down. So there will be no absolute min. But there will still be an absolute max. There's still going to be a highest point up here somewhere. So we're looking for an absolute max. So that's, again, back to what I was discussing earlier, the approach. First, consider the end behavior to determine which kinds of absolute extrema will occur, and then find the locations of those extrema. So now we know that we're looking for an absolute max on this interval. Where do we look? Well, let's go back up and look at Theorem 2 again. Absolute extrema, if they exist, must occur at critical numbers or at endpoints. For our function, we have these 3 critical numbers, 0, -3, and 2. But in this interval, the only critical numbers are 0 and 2. But we have now this new thing. We have this endpoint, x equals -2. So Theorem 2 tells us that the absolute max that we know is going to occur will have to occur at either that endpoint, x equals -2, or at one of the critical numbers that's in our interval. So Theorem 2 tells us that the absolute max must occur at either an endpoint or a critical number in the interval. So let's make that list of important x values. So there's our list of important x values and the corresponding y values. Now, again, we're looking for an absolute max. It has to occur, and it's got to be at one of these 3 places. So we just simply identify the greatest one of these y values, that one, and we make a conclusion about it being the absolute max. And again, it's worth concluding that the function will not have an absolute min. And there's our solution. Let's go on. Question C says, illustrate your results of A on the given graph of f of x. Now I see that there's a mistake here. I've got the axes wrong. Cross this out. So the results of A were that the absolute max on this interval, negative infinity to infinity, is y equals 194, and it occurs at x equals negative 3. So we should just label a point on our graph. Okay, let's go on. Question D says illustrate the results from B on the graph. Again, I've got the axes labeled wrong. Well, the question B was about the extrema on this interval from negative 2 to infinity. We found the absolute max was y equals 133 at x equals minus 2. So we should label a point on the graph there. Now, how do we convey what we're saying about that point? Well, maybe we should just draw the part of the graph that this is the max for. So that point, negative 2, 133, is not a place where there's a horizontal tangent. It's an absolute max because it's the highest point in the graph, and it happens to occur at an endpoint. Well, that's the end of that example. Let's go on. Now, in that example, we had a familiar function type, a polynomial, and we were able to determine which kinds of absolute extrema would occur just by reasoning about the shape of the graph. Now, of course, the fact that we didn't have to do any calculations to determine which kinds of extrema would occur doesn't mean that that determination was easy. We had to know that the approach should be to think about the graph shape. Now, what about cases where the function is not a familiar type, so you cannot determine which types of absolute extrema will occur just by reasoning in terms of the graph shape? Well, that's what we're going to do in this example. Example 2 is similar to a couple of your homework problems. For this function, find all the absolute extrema on the interval from 0 to infinity. So notice, this is not a familiar function, and it's not a closed interval. So that means that we are not guaranteed that there are going to be any absolute maxes or mins, and we can't reason in terms of the shape of the graph because we don't know the shape. So what do we do? If we can't reason at the beginning about what kinds of extrema we know we're going to have, what do we do? Well, let's go back up and look at our theorem. Theorem 2. Again, if there are any absolute extrema, they must occur at critical numbers or at endpoints. Well, we don't have any endpoints, but our only hope here is maybe there are some critical numbers, and maybe we can figure out something about what goes on at those critical numbers and figure out whether they're absolute maxes or mins. So we are led to needing to find critical numbers. We'll do that on the next page. So we need to find critical numbers for our function. That means we're going to start by finding f prime of x. But notice that this function is not in a good form for finding the derivative. It's in positive exponent form. Let's convert this function to power function form. Now that we have the function written in that power function form, we can find the derivative easily. So there's our derivative. Now we need to look for x values where f prime equals 0 or f prime does not exist. So that is, we're looking for partition numbers for f prime. We'll do that on the next page. So we can see right away that there is one partition number for f prime of x, that's x equals 0. That's because f prime parentheses 0 does not exist. Now that's not in our interval, so we don't really care about it, but it's good to find it. Now, what about partition numbers of the other kind? Are there any x values that cause f prime to equal 0? So we see that x equals 5 is a partition number because f prime parentheses 5 equals 0. So our partition numbers for f prime are x equals 0 and x equals 5. Now we are looking, though, for critical numbers for f of x. So that means a number that's a partition number for f prime that is also in the domain of f of x. So we have to see if f of x exists. We see that f parentheses 0 does not exist because you can't divide by 0. What about f of 5? So f of 5 exists. So that means that x equals 5 is in the domain of f of x. So x equals 5 is the only critical number for f of x. So remember what we're doing. We're trying to find absolute extrema. They can only occur at critical numbers, so we found the critical numbers. There's only one. X equals 5 is the only critical number. So if there's an absolute max or a min for f of x, it's got to occur at x equals 5. Well, we'll investigate that on the next page. So we don't know how our graph looks. We don't know if it's going to have any maxes or mins, but we do know that if there are any maxes or mins, they would have to happen at this critical number x equals 5. So now what? Well, let's consider the increasing-decreasing behavior of f to see if we can get a handle on the shape of the graph. So in other words, let's make a sign chart for f prime of x and use it to determine the increasing-decreasing behavior of f. Okay, so we're going to make a sign chart for our f prime of x. And it's on the interval from 0 to infinity. So there's our number line. Notice that the number line only has to go to x equals 0. And that endpoint is not included. So we're interested in this number line going to the right from x equals 0. So let's get some test numbers. So this is interesting. We found out that f prime is positive on this whole interval from 0 to 5 and negative to the right of 5. So what does that tell us about the increasing-decreasing behavior of f? We'll do that on the next page. So our function f of x is increasing on that left interval, and then has a horizontal tangent right at x equals 5, and then decreasing from 5 to infinity. So we can see that, therefore, at x equals 5, there's going to be an absolute max for that interval. Now, we're supposed to find the max. That means to find the y value. Now we already found the y value. It's that y value that we computed earlier. F of 5 is 25, so that y value is the max. Let's write a conclusion. So there's our conclusion. On the interval from 0 to infinity, f of x has an absolute max of y equals 25. It occurs at x equals 5. It's worth saying, I guess, as well, that f of x does not have an absolute min on that interval. So there's our conclusion. Question B is to illustrate what we just found on the given graph of f. Well, let's go back up. We found that there is an absolute max at x equals 5 and the y-coordinate is 25, so we should just label that point. So that's the end of that example. Let's go back up and review how this started. We started this by wondering about examples where we don't have a closed interval and the function is not a familiar type, so you can't determine, you don't have an idea at the beginning of the shape of the graph. What do? Well, so what we did was we started by looking for critical numbers. We found the critical numbers was just x equals 5. And then we investigated the behavior of the graph by studying the sign behavior of f prime. And that told us the increasing, decreasing behavior of the function. So without much at all to go on at the beginning, we were able to answer this question. Now I want to talk about what's called the second derivative test for local extrema. In section 4.1, we learned how to determine the location of local maxes and mins by studying the sign behavior of f prime. We used the first derivative test for local extrema. We looked for behavior like this in the sign chart for f prime, places where f prime changed from negative to positive or where f prime changed from positive to negative. There's another useful tool for determining location of maxes and mins. This one involves studying the sign behavior of f prime and f double prime. This is called the second derivative test for local extrema. And the idea is this. If you have a place on the graph where f prime is 0, so you have a horizontal tangent, and f double prime is positive, so the graph is concave up, well then you can see that that place on the graph is going to be a local min. On the other hand, if you have a place in the graph where f prime is 0, that is a horizontal tangent, and f double prime is less than 0, that means your function's concave down, then you can see that that place in the graph is going to be a local maximum. So over here we have a local min, and over here we have a local max. Well, so the second derivative test is just sort of making note of that. If you have a place on the graph where f prime is 0 and the second derivative is positive, then you have a local min. On the other hand, if the second derivative is negative, then you have a local max. So that's these two cases. If the first derivative is 0 and the second derivative is 0, then the test does not apply. The second derivative test can't be used in that kind of situation. Now this situation where the test does not apply, what does that mean? We should think about why it would not apply in those cases. So let's think about these three functions. F of x equals x to the fourth plus 5, g of x is minus x to the fourth plus 5, and h of x is x cubed plus 5. This should say equals x cubed plus 5. Now let's think about the derivatives of these functions. So here's f prime and f double prime. Notice that when x equals 0, both of those things are 0. Here's g prime and g double prime. Notice when x is 0, both of those things are 0. And finally, here's h prime and h double prime. Notice when x equals 0, both of those things are 0. So those are all functions for which the second derivative test does not apply. The second derivative test does not tell us whether there is a local max or a local min for those functions at x equals 0. Now, why not? What's wrong with those functions? Well, let's consider the graphs of those functions. Here's the graph of f of x equals x to the fourth plus 5. Here's the graph of g of x minus x to the fourth plus 5. And here's the graph of h of x, x cubed plus 5. So we can see that f of x has a local min at x equals 0, g of x has a local max at x equals 0, and h of x does not have a local max or a local min at x equals 0. So it's possible for a function to have first and second derivatives that are both equal to 0, and for that function to have a local min, or to have a local max, or to have neither at that x value. So that's why the second derivative test does not apply in such a case. So what would you do in such a case? Well, you'd use the first derivative test to figure out if there's a local max or a local min at that x value. Let's go on. So for example, this is an example similar to 2 of your homework exercises. Suppose you have a function f of x and it's continuous on an interval that contains the number x equals 7, and you know this stuff. F prime parentheses 7 equals 0, and f double prime parentheses 7 is less than 0. So the question is, describe the behavior of the graph of f of x at that point. Well, according to the second derivative test, since the first derivative is 0 and the second derivative is negative, that tells us the graph is concave down, so there's a local max at that point. So f has a local max at that point, and the value of the max is the y value, y equals f of 7. Let's go on. Now there's a second derivative test for absolute extrema, and that's this. Second derivative test for absolute extrema on an interval. It goes like this. Suppose that you have a function that's continuous on an interval with only one critical number in that whole interval. If you have f prime equals 0 and f double prime less than 0, that means that you have a horizontal tangent at some number c and the graph is concave down. Well, then that tells you, the second derivative test tells you that that y value, f of c, is the absolute max on that whole interval. Not just a local max, it's actually an absolute max on that whole interval. Similarly, if f prime parentheses c is 0, so a horizontal tangent at x equals c, and f double prime is greater than 0, so the graph is concave up, then f of c is the local min of the function on that interval. So it's very commonsensical just by looking at these pictures. So the last thing I want to do is go back and revisit the example we did before, studying this function f of x equals 55 minus 4x minus 250 over x squared. In question A, we found that f double prime was equal to 0. That was the partition number for f prime, and that was a critical number for f of x. Then we made a sign chart for f prime. So we made this sign chart for f prime. We used it to determine where f was increasing and decreasing, and we used that to determine that f of x had a local max at x equals 5. Well, what I want to do here is redo that investigation using the second derivative test. That is, having determined that f prime parentheses 5 is equal to 0, don't proceed to make a sign chart. Instead, use the second derivative test to determine the absolute extrema. So remember our results. Now we're supposed to use the second derivative test. that means we're going to need to find the second derivative. Now for that, we'll use the power function form of f prime. So there is our formula for f double prime of x. Now what are we supposed to do with this? We're supposed to figure out if f double prime parentheses c is positive or negative at x equals 5. Negative 500 over 5 to the fourth. What is 5 to the fourth? Well, that's messy, right? 5 squared is 25, 5 cubed is 125, 5 to the fourth is 625. Well, wait a minute. All we care about is the sign. We have, this should be negative 1500. We have negative 1500 over 5 to the fourth. So in other words, negative 1500 over something positive. So the result is going to be negative. So let's write our conclusion. So our conclusion is that since f prime parentheses 5 is 0 and f double prime parentheses 5 is negative, and because we know that that is the only critical number on that interval, then that must be the location of an absolute max for the function. So now we have two ways of finding this absolute max. We have this method that we just used using the second derivative test, and then the method we used when we first solved this problem by the method involving studying the sign behavior of f prime. Well, that's the end of that example, and that's the end of this video. Thank you.